Benjamin Ménétrier from Toulouse in France. So I'll talk today about the BUMP library, which is the first library we have in the Sabre repo on the GitHub repository Sabre, so for B matrices. So to start, I'll give you some basic facts about the B matrix and about variational DA. First, we all know that the background error modeling is really a key feature of variational DA systems because it is the last operator applied to define what will be the final increment. So it really spreads the information coming from the innovation, so the difference between the guess and the observation, and it spreads this information across spatial and temporal dimensions. So it also ensures that the analysis is well balanced. So it's pretty important. We don't need to store the whole background error covariance matrix. Well, actually we can't because it's really, really big. If your model state is like 10 to the 12 or 10 to the 9 elements, the B matrix would be 10 to the 18. So that we can't store or evaluate this kind of matrix. What we need for variational systems is just to be able to apply B on a state vector. And that's all we need to do. To ensure that B is symmetric and positive, the common practice is to build its square root denoted U, and we apply successively the adjoint of U and then U itself, and so we are sure that B is symmetric and positive. So there are basically three general approaches to build a background error covariance model. The first one is the static B. It's a sequence of parameterized operators. The second one is the ensemble B that uses an ensemble of perturbed forecasts to sample the background error covariances. And these two models can be combined combination, so to give the hybrid B. All covariance models will require a smoother to spread this information across spatially, and so in most implementation it will be grid specific, but here we will see that BUMP includes a generic smoother. So let's start with the BUMP library. So BUMP means background error on structured mesh package, and it's a generic tool for covariance modeling. I've been developing it since 2015, and so BUMP can work with any kind of grid: Gaussian grid, cube sphere, unstructured, limited area, ocean, any grid. And so it can also take the boundaries into account for the ocean. So it is designed to integrate two aspects of covariance modeling. The first is the diagnostic of the required parameters, and then it's the efficient application of this covariance model. So BUMP includes its own smoother that is called NICAS for normalized interpolated convolution from an adaptive subgrid. So basically the code is written in Fortran 90, even if Yannick would like to change that. And it has about 25,000 lines. So recently, last year actually, BUMP has been included in a common repository called Sabre for system agnostic background error representation. And we hope to add more covariance models into Sabre very soon, for instance, spectral or recursive filters. So BUMP is fully interfaced with OOPS, and so you can basically use BUMP by specifying some specific parameters in the YAML files configuration. I think you will see that in the practical. So the real core of bump implementation is subsampling, because we know that high resolution grids are really great for model dynamics, but they are very costly, and for data assimilation they are not always useful, especially for background error covariance modeling, because we want to spread information, and having a very high resolution grid is not always a good thing. So in general, the size of the background error structure that we want to represent is really larger than the model grid cell size. And so the basic ideas behind BUMP are, first, to subsample the model grids, so extract a random subgrid from the original grid to work, perform all the costly operations on this subsample mesh, so to reduce the cost, and finally interpolate the results on the full resolution model grid, but just at the end. So so today I'll just talk about the static B, and then about the ensemble and hybrid B, and tomorrow morning I'll talk about the Nika smoother and the bump usage. So let's start with the static B. So the static B should be really a high rank and robust operator, and it is based in general on a sequence of parameterized operators, and these parameter operators can be estimated using an ensemble or specified with user-defined parameters. If you use an ensemble over a long period, you can get a climatological estimate of the B matrix, which will be more robust, but not so specific about what errors it represents. And if you do the estimation over a shorter sliding window, you'll get a more flow-dependent static B, but it will be more noisy too. So the most common static B model, the most simple, is the one with this first equation. So where C at the center is a correlation matrix. Then on both sides of this correlation matrix, you have sigma, which is just a diagonal matrix with the standard deviations. And it contains the standard deviations of each variable. And finally, the KP operators on both sides are the multivariate balance operator. And KP is very important to get balanced analysis and reduce the speed up of the following forecasts. So it should be noted that with this model, it's very simple to define a square root of B if we have a square root of C. So we just get the formula in 2. Oh, sorry. Yeah, here. So bump can be used for these 3 operators. So the correlation length scales in the correlation matrix are generally estimated either globally or locally, and they are used to set up the Nika smoother. It's important to notice that C is a correlation matrix, so its diagonal coefficients should be 1. And with most other modeling of the smoother, it's kind of difficult to get this exact normalization at 1 on the diagonal. But with MICAST, it's possible to do it exactly at a low cost. Then the standard deviations, they are estimated also locally, and they are potentially filtered. So it's just a field of variance of your ensemble that you filter and then take the square root. So there is an objective filtering method developed in some paper I did 5 years ago. and that are implemented in bump. The vertical balance operator is computed in bump. We just use vertical regressions between the different variables. So it's just a part of a more complex balance operator, KP. KP can be quite complex and quite model dependent. So what's in bump is just what could be generalized for all models, but I think for most applications we will need a generic part that is in bump and a more model specific part depending on the variables that are used by the model. So in this OOPS framework, the different static B components can be used either from bump or from your own model, and you can combine them as you wish. For instance, you could use your own correlation metrics and use the standard deviations computed by bump, and maybe a vertical balance computed by bump too. So really with this configuration files, the YAML files, you can configure everything and choose what you want. So now I'll talk about the ensemble and hybrid B. So it's going to be a bit more technical, but I will try to, so you will see some illustrations to understand. The main issue with ensembles is the sampling noise. So first we have to understand that we have an ensemble of forecasts to estimate the sample covariance matrix, and we compute the perturbations with reference to the mean, and we could denote full B here, the asymptotic sample covariance. So basically it's what we would get with an infinite ensemble size. Of course, we don't have an infinite ensemble of forecasts. In general, we just have maybe 50 or 100 or maybe 200 if we are rich, but no more number. But we can, for the mathematical derivations, we can define this asymptotic sample covariance that we would get with an infinite ensemble size. And it's very useful to define the sampling noise. So the sampling noise is just the difference to the B here, the last equation. It's just the difference between the actual sample covariance that we have with our real ensemble and the B that we would get with an infinite ensemble size. So I want to show first that the sampling noise strongly depends on the ensemble size. So here on the left panel, you can see the true covariance matrix of a very simple system. It's just a 1D system. So the covariance matrix is just 2D. And there are just 100 grid points on a circle. So it's very, it's not even a model. It's just a very simple circular system for illustrations. And in the central panel, we have 10 random draws using this true covariance matrix on the left. And if we compute the covariance matrix, the sample covariance matrix from these 10 members, we get the right panel. So we can recognize some features of the left panel, but there is a lot of sampling noise. But if we increase the number of ensemble members to 20 or 30, we see that on the right panel, the sampling noise is getting smaller and smaller. And so I can increase 50, 100 members, 200, 500, 1,000. So if I could have 1,000 members, my sample covariance on the right would really represent the true covariance I started with on the left. But as we say, it's an old commercial we had in France in the 70s. We say we don't have oil, but we have IDs. And it's the same here. I mean, if we had 1,000 members we could just use it and it would be fine, but we don't have 1,000 members, so we will need to be a bit more clever. And the first thing to do is localize this covariance. So we can do a localization with a short product. So it's an element by element product between two matrices. So it's very simple. You can see the equation here. So Bij is just the element by element product of the localization matrix L and the sample covariance matrix B tilde. And in practice, L will damn the long distance correlation that are pretty small and that are so more affected by sampling noise. That's why we call that localization. So here on the left, we have the sample covariance computed with 10 members. So it's all noisy. In the center panel, we have a localization matrix, and we just do a product element by element of these two metrics on the left and in the middle, and we get the right panel. So we can see that there is still some noise on the diagonal, but we have removed most of the off-diagonal noise. And that's exactly what we want to do with localization. So now the big question is, what is the optimal localization length scale? It's really critical because we can see here that on the left panel, it's still the sample covariance computed with 10 members. In the middle, it's the localization matrix, but here it's 1 everywhere. So it's basically no localization because we are multiplying all the elements of the sample covariance by 1. So we get the same thing on the right. But now I will reduce the length scale of the localization matrix. And we can see that reducing this length scale, I have removed most of the off-diagonal noise. I can do it again. So no localization. And then we reduce the sampling noise. You can look at on the right panel, we reduce the sampling noise. But if I continue reducing the localization length scale, well, then I'm just losing the signal that is of the sample covariance matrix. So the important thing, it's to compute the right localization length scale to remove the noise but keep the signal. A second solution to remove some sampling noise is to add a contribution of a static covariance matrix. So we just do a linear combination with two coefficients beta E and beta S, and so we combine basically the localized ensemble covariance matrix and a static covariance matrix. So in the illustration on the left, we have the localized covariance. In the middle, it's the static covariance. And on the right, it's a 50-50 hybrid. So we can get some features back that are being lost maybe in the localization. So it's really an interesting solution for most variational systems. And similarly, we have an optimization problem because we don't know what the weights between the localized covariance on the left and the static covariance in the middle should be. So we did a 50-50, but here in this example, it's 100% on the localized covariance and no weight on the static covariance. Here it's 75 and 25, 50-50, and 25-75. So we have to find a balance between the localized covariance and the static covariance. So to optimize the localization and the hybridization, I developed a method because most methods, existing methods, were empirical and quite costly. It was like brute force optimization or OSSEs. And so I wanted a method that could use only the ensemble members, no observations here, that would be affordable for high-dimensional systems and generic enough to run with all kinds of grids. And so if we consider the equation of the hybrid B. So it's basically a linear filtering of the sample covariance. So we apply the ensemble weight and the localization matrix on the sample covariance, and then we add a static contribution. So if it's a linear filtering, we have methods to optimize the weights. But for this optimization, we would need the asymptotic sample covariance, so the B metric that we will get with an infinite ensemble size, and we don't have this one. So we have to use some theory to express expectations and statistics about the asymptotic sample covariance using only the real sample covariance that we have with a limited number of members. And so the two objectives of this theory are to express the linear coefficients of the filtering, minimizing an error that is shown here, and we use the linear filtering theory for that, and also to express the statistics on asymptotic quantities that are unknown with expected sample quantities that are at least computable. And for that, we use the centered moment sampling theory, even in a non-Gaussian case. So the sampling noise is, as you can see, the sampling noise is, here we have an example for the sampling noise properties. On the left, we have a true covariance that is homogeneous. So it's the same for all the same covariance for all points. And the sample covariance is in the middle with 10 members. And I just do the difference between the two, and I get the right panel, which is the sampling noise. Here I changed the true covariance with a smaller variance on the top right quarter and a higher variance on the bottom left quarter. And we can see that the sample covariance is changed also, and the sampling noise is smaller in the areas where the true variance is smaller. Now I change not the variance, so not the value of the diagonal, but the length scales of the true covariance on the left. And we can see that for the sample covariance in the middle, the length scales is larger on the bottom left quarter and smaller features on the top right quarter. And we can see the same behavior for the sampling noise. So what's important to understand is that the sampling noise length scale is really related to the asymptotic length scale. And we can use this feature and a lot of math to find what should be the optimal localization. So if we don't have any hybridization, you can see here the first formula that use expectations of products of sample covariance coefficients, and also the strange Greek letter in the second line on the right. The capital C is the fourth order centered moment. And now if we use an hybridization, we also need to compute the two weights on the static and on the ensemble contributions. And on the bottom left, you can see the formula for the static weight, and on the bottom right, the formula for the ensemble weight. And basically, the idea of BUMP is that, well, even if this theory is nice, nobody would like to implement this kind of math formulas. So I wanted to build a code that could do that for everybody and be usable on any kind of grid. So here we have an example of the Fv3 grid. And so it's very dense. It's a C180 grid, so it's a full model grid. And we can't really apply BUMP with this on this full grid. So the first step will be to subsample the grid. Okay, so the blue points are just the subsample of the full grid we had before. Then we will define some couples of points. So for each blue point we had before, we define neighbors at a given distance, for instance, around 100 kilometers. And then we define other couples around 200 kilometers, and then other points around 300 kilometers from the initial blue points. And we will use all these diagnostic points to compute couples and compute the formulas I showed you before. And so for each couple of points, BUMP will use the ensemble to estimate the sample variances, the sample covariance, and this famous fourth order tangent moment. This one is needed for non-Gaussian statistics. So that's the first step. Then we will do a local averaging. So here the red points are selected, and we will average the diagnostics we've done in the previous steps around these red points. And with the spatial and angular ergodicity assumption, we will average locally the values we computed in the previous steps to get estimations of the following expectations here. And these expectations are the ones we find in the formulas. And once we have these quantities, we can compute the localization function and the hybridization weights with the formulas I showed you before. So here is a simple example. The red points is the center of the averaging area, and the light blue point are all the subsample point, but we will only consider the dark blue points for averaging here. And we'll use the first class here. The green points are show the couples for first class around 300 kilometers, and then a second class around 400, and so on and so forth. And so what we see on the right of this panel is the localization function that is computed progressively for different distance classes. So I'm sorry it's a bit fast and a bit complicated. I have some documentation and videos to show that a bit slower. But finally, what we get is a localization function. So we are happy, but well, we're not sure it's positive definite, and it's not completely smooth. So we will first do a fit of this localization function. And for that, we use the Gaspari and Kohn 99 function. It's a very widely used function in data assimilation. It's basically like a Gaussian, but with a finite support. So it's better for some applications. And here the finite support of the function is around 1,455 kilometers. So we get this length scale, and we will get this localization length scales for each of the red points we had in the previous maps. And so now we have this value at each of these points, the localization length scale, and we can interpolate to get a localization length scale field. And we couldn't have done the diagnostics on each point of the Fv3 grid because it's too big, but we can do it on a subsample grid and then interpolate back on the full grid, and then we get this localization length scale map at a reasonable cost. So this is the HDiag driver of BUMP, so it's for hybrid diagnostics. First, you define a homogeneous sampling of the model grid. Then for each point, you find distant points for a series of distance classes. Then for each local averaging center, you will compute some average, compute the localization and hybridization weights using the formulas, and then fit the localization to get a localization length scale. Finally, the last step is to interpolate the localization support radius and get also the hybridization weights over the model grid. So to finish for today, I have a simple example of the sensitivity to the ensemble size. Here it's an example where we compute the localization length, the localization function in color with for different ensemble size. If we have only 25 members, the localization function is narrow because we will have a lot of noise, of sampling noise, because we don't have many members. And so we prefer to, okay, reduce the signal, but remove the noise far away from the origin. But if we have more members, like 50, 100, or 150 members, then we can increase the localization length scale because we are more confident in the sample covariance, we have less noise. So the curves you see here are given from the bump diagnostics, and they are consistent with what we would expect. And finally, this is the static covariance weight and the localization covariance weight, so the hybrid weights, depending on the ensemble size. So the x-axis is the ensemble size, and the more members we have, the more weight we can put on the ensemble covariance, the localized one, and the less weight we will put on the static covariance because we don't really need it if we have a big ensemble. So this is the final summary. So the message you should keep home is just that the sample covariance, it's great because we can get some flow-dependent covariance matrix with an ensemble, but it's affected by sampling noise. And this sampling noise decreases if the ensemble size increases, but we are not rich enough to get super big ensembles. So we will need to apply localization and hybridization to filter out the sampling noise. The asymptotic sample covariance in this theory is the filtering target, but we don't know it. It's what we would get with an infinite ensemble size. But we can combine the linear filtering theory and the centered moment sampling theory to get this nice formula as I showed you before. And so combining these theories leads to practical formulas for both optimal localization and hybridization weights. And we can compute robust estimates using ergodicity assumption. So that's what I showed you, the couple of points on the map. But these statistics can be computed either globally on your domain or locally with these local averaging centers. And finally, we can get either global or local estimates of the optimal localization and hybridization weights. And I think that's all for today. Tomorrow we'll talk more about the NICA smoother, and I'll give you a few examples of how to use bump in an OOPS configuration file. Thank you.